something like a purely data-driven approach may be very popular in the guy from maybe a machine learning approach. And this is actually one of the very major direction of research, and there are many research on this using this approach. But the problem will be, of course, it requires large amount of training data. This might not be affordable, especially in wireless communication systems. So that's why we consider, okay, maybe we can utilize the merit of both these two different approaches, meaning that we still utilize this multi-layer structure here by taking advantage of domain knowledge. And then we control these parameters by using machine learning or data-driven approach, or I should say using the deep unfolding approach. So this is a basic idea of this study. Then that's why we have considered, or maybe the purpose of this study will be something like this. In order to confirm this approach, we have considered the signal distortion compensation for frequency domain equalization systems such as OFDM or something, because current communication systems are basically based on this kind of approach, and which is suffered from transmitter and receiver IQI and also carrier frequency offset. Okay, this is the main focus or purpose of this final part of this matter. Okay, and yeah, in order to explain the detail of the content, let me firstly review of frequency domain equalization system. I think that many of you are familiar with this kind of approach, but just in case, let me explain. Okay. And here we consider two different kinds of frequency domain equalization systems. One is SCCP, other is OFDM. Okay. And the first one, this SCCP, in this system, we transmit the signal as a vector, or maybe I should call it block or something. Okay? So S is a kind of vector. Okay? And before transmission, a kind of redundancy called the cyclic prefix is added to this vector. And this operation can be represented by using a matrix. So if we multiply this in the TCP, this is a matrix. If we multiply this one to this vector, then we can obtain this CP added transmission signal. Okay? And then channel is assumed to be a channel, frequency selective. So that's why this matrix stands for a convolution matrix, which has a triplet structure. Okay? And then at the receiving side, this cyclic prefix part is removed, again by using this matrix multiplication. Okay? And then we obtain the final receiving signal. Here, for simplicity, we just ignore the noise, but the idea is basically the same. And the point is that by using this processing, the channel, including this CP operation, it can be represented or maybe can be given as a second matrix channel, right? As far as this cyclic prefix is enough, okay? Okay. And again, and then this second matrix can be diagonalized by using DFT matrix. So that's why we can replace this part with this mathematical expression. Okay? So that's why the impact of the channel can be compensated by using this kind of frequency domain equalizer, which has almost the same structure as this channel part. So the difference is that here DFT is actually DFT is a unitary matrix, and so that's why the multiplication between these two guys results in just an identity matrix. And here this is a diagonal matrix. So if you utilize the Delphine criterion for this matrix, so this can be an inverse matrix of this lambda. Okay? So if you multiply these two guys, then which results in just an identity matrix. And again, these two are identity matrix. That's why which results in the identity matrix. So that's why if we have no noise, in that case we can perfectly reconstruct the transmit signal at the receiving side. The point is that this DFT, of course, not the multiplication DFT, but actually the FFT is utilized in the receiver, of course, because it is very computationally efficient. And also this guy can be also implemented by using the fast Fourier transform. And this is just a multiplication of diagonal matrix. So that's why the computational complexity is very, very low. So this is the reason why this approach is widely used in wireless communication systems. Okay. And then let me explain a bit about distortion model of IQI. Just forgetting about FD system, frequency domain equalization system. This is just for the IQI, in-phase, quasi-phase imperfection and its compensation. Okay? And here, this is a bit complicated equation, but what I want to say here is that here X is the original signal, so before distortion. And this X tilde stands for a signal distorted by this IQI. Okay? This distorted signal can be represented by using this kind of weighted sum of X and its complex conjugate. Right? If alpha equals 1 and beta equals 0, which means that there is no distortion, right? Because X tilde is equal to X. But if you have a kind of impact of IQI, then the distorted signal is represented by using this one. And here, alpha is not 1 and beta is not 0 in that case. Anyway, this kind of expression is often called widely linear relation in the signal processing. And we utilize this function G alpha beta for this distortion in the lesson market talk. And this is a bit complicated, but actually the distortion by this IQI can be easily compensated by using this widely linear filter. What is widely linear filter? It is, here we have as an input signal, we have a distorted signal here. Okay? But not only this, we also have its complex conjugate here. This is actually a key issue, a key point of this compensation. And this is the reason why it is called widely linear filter. Okay? With this expression, we can simply multiply some matrix from left-hand side. Actually, if you utilize the zero forcing criterion, this is actually this one, very, very simple matrix. It is a scalar multiplied by, scalar is multiplied to this identity matrix. It's very simple matrix. So by using this kind of matrix, we can perfectly compensate this kind of distortion. Okay? And then let me also explain a bit about distortion and its compensation for the case of CFO, frequency offset. It is very simple. Here, this R is an original signal, and this one is a distorted signal due to this CFO. And the relation is very simple, just this diagonal matrix, which have its kind of phase shift on the main diagonal part, and then we obtain this distorted signal. So that's why compensation can be achieved by using the inverse of this one. Formally, just this part is just a minus. Okay? So basically, the diagonal matrix multiplication can compensate this one. Okay, now I'm ready to explain the detail of our proposed method. Okay? Now, we want to consider the distortion compensation for this SCCP system, which suffers from this transmit and the receiver IQI and CFO. Okay? And actually, this the first figure stands for the actual distortion model or block diagram of the system. And here, this is a transmitted signal, and this is a CP addition. Okay? And then, before the channel, actually, at the transmitting side, we have kind of distortion due to transmit IQI. Okay? And then, a channel matrix has a kind of impact on the signal, and then at the receiving side, the CFO and also the RX IQI will distort the signal. And finally, we remove the cyclic prefix, then we obtain the signal. The point is that actually our idea is, as I explained firstly, our idea is maybe this one. So we want to compensate each distortion independently, maybe in a reverse order. So in order to achieve this kind of approach, this distortion should be a kind of decoupled. Actually here, this CP operation here and this green colored processing, and these distortions are kind of in mixture, right? So this can be problematic to our approach. So that's why we consider to decouple these distortions here. Okay? And the point is that actually this distortion due to IQI, so G, function G, is actually a commutative. We can change the order with real matrix multiplication. And as you know, this CP addition, this TCP is a matrix of real number. So that's why we can exchange the order of these two, as shown in this figure. Okay? And also here, receiving side, so these two. So this RCP is also the real matrix, and we can exchange order of these two. And also this one, this delta F is actually how can I say, it's a complex matrix, but this is a diagonal matrix. So we can easily exchange the order. Also the size will be a bit changed, but almost the same. So that's why we can change or commute the order of these distortion and the matrix multiplication as this figure. Then, now here we can see that, okay, this part will be original on the ideal case of this SCCP transmission. That's why we can replace this part with circuit channel matrix. That's why the equivalent channel model after decoupling can be shown as this figure. Okay, this is actually same as this, the first line of this part. This is the same one. I mean that, okay, the kind of equivalent transmission model will be something like this. The transmit signal is distorted by TX IQI, transmitter IQI. Then the channel, second channel matrix, and then CFO, and finally receiving side IQI. And that's why we can compensate these distortions with a reverse order. I mean, at the receiving side, this is the same signal. First, we compensate this RX IQI at this filter, and then we compensate this CFO at this filter. And then we perform FDE to compensate this second channel. And finally, we compensate the transmit IQI. That is the basic idea using the multi-layer filter. And of course, in order to achieve this kind of compensation, we need distortion parameter for each filter. So that's why, by using the domain knowledge of this configuration, we compose this kind of multi-layer adaptive filter. So this part corresponds to this one, this part corresponds to this one. So each part corresponds to this filter. And each filter, the structure of each filter is taken from the domain knowledge of each compensation filter. For example, this in the first filter, we know that, okay, IQI, receiver IQI can be compensated by using this kind of filter. That's why we have constructed the filter which has structure that some kind of scalar, that is a random parameter, scalar times identity matrix, and scalar times some identity matrix. So we can have only two parameters in the system. So we can reduce parameters a lot. Okay? So in this way, we can design or reflect the domain knowledge in the filter design, and we control all parameters by using the idea of the deep unfolding. This is a basic idea. Okay? And yeah, basically, actually, this is almost the end of my talk, but in the case of OFDM, there is a little bit more, we need some kind of idea, actually, in this case. Actually, in almost all typical signal processing cases, basically there is also no difference between the SCCP and OFDM by. But in the case of this IQI compensation or something, there is a little bit of difference. Anyway, let me explain. In the case of OFDM, the difference from this SCCP system is that we have IDFT at the transmitting side and also DFT at the receiving side. So that's the only difference, basically. And by using some kind of manipulation, we can finally obtain this very simple channel model. Here, this is a transmit signal, and the receive signal is just obtained simply multiplying the diagonal channel matrix. Very simple. However, in this case, if we have this kind of multiple distortion, we have this kind of block diagram. Almost the same as the SCCP case, but we have IDFT here, and this is the DFT. As in the case of SCCP, we firstly change the order of this transmitter IQI and the CP addition matrix, as shown in this figure. Okay? And also we exchange the orders of these three at the receiving side with, as shown in this figure. Okay? But in this case, there are two problems here. One is this one. Here, we have IDFT matrix here, but this guy is, of course, complex matrix. So that's why the distortion due to this transmit IQI and this matrix multiplication is not commutative. That could be a problem. And also here, these are the same actually. But actually, this in the receiving side, this is a received signal in the frequency domain, but this is a received signal at the time domain, right? So we can also utilize this time domain signal. So that's why we can firstly compensate these two distortions, and then we can consider DFT. So that's why we can cope with the problem of this receiving side. Okay? The problem will be this one. We have to come up with some idea to cope with this kind of non-commutativity. But actually, this can be tackled actually, meaning that okay, this is the original distortion process. I mean, this transmitted signal S is multiplied by this IDFT matrix, and then after that, the distortion of IQI is found. Okay? So this is the original order. Okay, but actually, with some kind of manipulation, the order can be exchanged as this expression. Here, the transmitted signal S is distorted with some kind of this expression. Then, after that, this distorted signal is transformed by using the IDFT, right? And here, you can see this distortion model is somewhat similar to the transmitter IQI, but the difference is that we have D square here. If we don't have this D square here, then the distortion is exactly the same as the IQI distortion. But if we introduce this kind of a bit different distortion, we call it DFT mixed TXIQI, but if we introduce this kind of a bit different distortion, we can change the order of these operations and the distortion. And this distortion can be also easily compensated by using very similar matrix, as in the case of purely this IQI distortion. Here, difference is only, again, here. Originally, this part of identity matrix, so we can replace it with D square. Actually, D square is something like a shifting matrix. It's a very simple structure matrix. So that's why if we introduce this kind of a bit different type of distortion compared to the original IQI, we can change the order of these two. Here, okay, I should write this is a DFT mix TXIQI, but the original distortion, and this was a bit different distortion here. By using this kind of expression, we can change the order of these two. And yeah, also we consider received signal at the time domain here. Okay. And by using this kind of idea, we can cope with the problem. And also by using this kind of bit manipulation, finally obtain this kind of decoupled distortion model, as in the case of the SCCP. And that's why we can utilize, this is a decoupled model, and this is the multi-layer filter to compensate with the reverse order of this thing. And this can be used to construct adaptive filter structure. That is a basic idea. Okay, and then let me show some numerical results from the proposed approach. And this is a bit rate performance of the SCCP system and OFDM system. And as you know, so in the case, this is a horizontal axis is the SNR, the vertical axis is the PR, so that's why the lower the better performance. And here you can see many curves, but actually this red colored broad line stands for the ideal case. So this is the case for the frequency domain equalization only, but there is no IQI distortion or no CFO. Okay. So this can be a kind of a baseline or best performance, okay, which we can expect. And here you can see the solid line with green color with maybe circle point, which stands for the performance of the multi-layer filter obtained as, for example, in the case of this one, but with the perfect information of the distortion parameters. Of course, this can be a kind of ideal case, but by using the perfect information of the distortion, we can achieve almost the same performance as the ideal case, the red colored line. Right? So, which validates some kind of appropriateness of the structure of the multi-layer filter derived with our multiplication, both in the case of SCCP and here OFDM case. Okay? And here, actually the third one, this green colored curve stands for the proposed method using this learnable multi-layer filter and using the deep unfolding approach. In this case, we have not assumed any channel information, including the impulse response. This was all parameters are thoroughly calculated by using the data-driven manner, I mean output error only. But in this case, we assume quite a large size of data set, training data set. Actually. And here you can see also this orange colored curves. And this is quite close. Actually, this is an existing method. And this is also based on somewhat model-based approach. But it requires more parameters compared to the proposed method because our method utilizes more rigorous, utilize domain knowledge more rigorous manner. So that we have succeeded in reduced number of parameters. That's why the proposed method achieves a little bit better performance in this case. Okay. But if we reduce the number of data set size, actually our merit of a proposed method is more visible actually. In this case, of course, there are certain kind of degradation compared to the previous case. But still, okay, this is a case of the data set size of C equal 4. 4 means that the number of single carrier block transmit, number of blocks or OFDM symbols is to be 4 or 2 or 1. Okay, so it's not that much, right? So only by using the 4 blocks training data, we can train all parameters, and with we can achieve this performance. Of course, in the case of only single transmitted block, the performance is quite bad. But by using 4 simulations, we can achieve maybe a lower performance can be achieved. In contrast, in the existing method, which requires a bit more parameters, the degradation is more severe in this case. Okay. Yeah, actually, these are the learning curves for the case of the small data set size. And here, this is a single carrier case, and it's a OLDM case. And the upper curve stands for the performance, learning curve of this proposed method, and the lower curve stands for the existing method. And here, this blue colored curve stands for the training loss, and this orange colored curve stands for the validation loss. As you can see in the lower figures, this is the existing method. You can see the separation between these two curves, which means that a kind of overfitting, problem of overfitting can be recognized in the case of the existing method. But in the case of the proposed method with C equal 4, for the size of the training data is 4, actually these two curves are not that separated, meaning that we can achieve good generalization performance thanks to the small number of parameters in the proposed method. And yeah, this is the final slide in black. Actually, with the proposed approach, because each filter corresponds to a kind of distortion for each distortion, right? So that's why by using the round parameter, maybe we can estimate the parameters of the distortion from the round data, maybe which enables us to monitor the channel, for example. And so that's why we have considered to estimate parameters in these distortions from the round data. That is the result, actually. And so far, I cannot say this is a good result, but okay, this is a SNR, so this is the error. For the case of carrier frequency offset, maybe the estimation accuracy might be good. And also, this orange curve curves the IQI parameter for the case of this solid curve, solid line. Okay, solid line are parameters for the receiving side. And on the other hand, this transmitter side is actually very difficult. It's a kind of far away. So the maybe estimation accuracy might not be enough, at least for the current form. But maybe there might be possibility to estimate or monitor channel impairments from just using these round parameters. Okay, that will be more future work of course. Okay, anyway, okay, this is my last of my talk. I have explained the signal decision compensation scheme using the adaptive multi-layer filter or FD system, taking advantage of the idea of deep unfolding. And the proposed method, all filter coefficients are determined solely by output to the final layer by using the backpropagation. And Yeah, proposed approach utilizes domain knowledge. That's why it requires very small number of parameters. That's why it can be controlled or trained with a very small number of training data, which might be beneficial, especially for the case of wireless communication. That's it. Thank you very much for your kind attention.
Okay, thank you, Professor Hayashi. Is there any questions? First of all.
Yeah, thank you, Professor Hayashi, for your very intriguing talk, okay, because you kind of explore the idea of an unfolding scheme, okay, to the kind of the conventional model-based approach. Okay. But my question is that, okay, is your scheme applicable only to the iterative evidence? Because when you say unfolding, which means you have a task executed repetitively, so you get unfolding, okay, so you have a wide, kind of the wide observation windows to do the optimization. So I think my first question is that is your scheme only applicable only to the iterative evidence? How about those non-iterative evidence, but still maybe still the multi-layer work? Okay, so is that still applicable? Okay. And then the second one is that when you say the deep unfoldings, okay, which means you have to kind of collapse, okay, many iterations into a big loop, okay. So the question is how deep, okay, should we unfold the evidence to achieve the best result? Of course, if we the unfolding factor is larger, actually it kind of collect more data, okay, for the optimization purpose, which might yield a better result. But in some sense, maybe it will kind of complicate the computation in each iteration. So maybe you use a few iterations to achieve to converge. But in each iteration, because of the complexity of your how we say that the loop bodies, maybe it actually takes longer to computations.
Thank you very much. A very nice question. For the first question, actually, this last part of my talk focuses on multi-area filter rather than the iterative algorithm, actually. So the answer will be yes, we can apply this idea of deep unfolding instead of iterative algorithm for the case of multi-area filter, but I'm not sure. Okay, we can find many iterative algorithms in the existing signal processing, right? But I'm not sure how about the multi-area filter. Is that the common? We can have many this multi-area structure in communication systems, but if we consider other kind of applications, I'm not sure it is possible to find any kind of structure or not. But actually, I call it a deep unfolding, but actually it need not to be deep. I think that actually, in the case of this optical communication, we have utilized only maybe 4 layers can be utilized for the idea of deep unfolding, actually. So in that sense, if signal processing can be represented by represented by using some steps, there might be a possibility to control all parameters by using the idea of deep unfolding. But the point is that, for example, even with very small number of layers here, okay, in that case, if you try to adaptively control each filter coefficient, the control of adaptive filtering is achieved or maybe employed for each filter. It is actually very difficult to control because if we control, for example, this parameter of this part, usually we control parameters just using the output of this part, right? So this part should be compared with some kind of supervised signal. But because typically we have many different kinds of distortion in the signal, usually this part have not only the distortion which corresponds to this filter, but also other distortion might be included in this part. So that's why the independently control each filter by using adaptive filtering is almost impossible with this approach. But by using the idea of deep unfolding, we don't have to care about this kind of issue. anyway, we want to make the final result to be maybe an ideal signal. So by using this fact, we can control each filter simultaneously. So in that sense, we don't need to have many layers. Even this number of layers can be 2 or 3. This approach could be beneficial. So that could be one answer for the first question. Is this okay? And for the second question, yeah, as you said, actually, usually we don't know how many layers are required a priori, because maybe we can firstly design, actually this, how can I say, the number of layers correspond to the actually number of iterations like discrete. So that's why maybe we can firstly design the number of layers based on the maybe original algorithm, how many iterations are required for the original algorithm. This can be a kind of maximum number of layers. And if maybe you can apply the idea of deep unfolding with this algorithm by using the maximum number of layers. And then usually you have much faster convergence for that case. But with this result, maybe you can adjust the number of layers. Okay, maybe you can reduce number of layers because we can achieve this kind of acceleration or something. So maybe we need some kind of this trial and error process will be required to control or adjust. But anyway, with this method, maybe you can reduce the complexity of the system. Yeah, that could be one possible approach for the second question. I hope this can answer your question.
Is there any questions?
I think I have a follow-up question.
Okay.
I think for the multi-layered filters, because you still use the adaptive filter, I assume it's adaptive filter. So adaptive filter is still can still be considered as an iterative algorithm because you have to iterate, okay, the filters, okay, the parameter to get the to get the convergence. So even though it's a different filters in different sections, but in each